današnju radionicu koju organizuje naš dugogodišnji prijatelj, kompanija i sponzor i neko ko je uvijek uz naš kongres, kompanija EnergyNet. I u tom celom kontekstu i dogovoru mi danas imamo na dnevnom redu jednu vrlo lepu radionicu, workshop, pod nazivom Dekarbonizacija zgrada pomoću održivih sistema toplotnih pumpi, zahvaljujući ljubaznosti kolege Fabricija Cervara iz Business Development Managera iz kompanije BlueBox by Swegon from Padova, Italy. I would like to once again introduce Mr. Fabrizio Cervaro. He comes from the well-known company from Italy, from Padova, and as the part of the high-level communication and high-level cooperation with the company EnergyNet. Okay, thank you for coming. Thank you for your presentation, and the floor is yours.
Thank you. And good afternoon, everybody. Welcome to all. I'm Fabrizio Cervaro. I come from Italy. I work at Swegon in the cooling and heating business unit that include the company formerly known as BlueBox. Nowadays it's called Swegon Operations SRL. We are based near Padua, I will say halfway between Venice and Padua in a nice region. My role in the company is business development manager, and I look after a number of geographies and countries, including Serbia and including EnergyNet. I'm very grateful to the organization, and I'm very grateful to EnergyNet for the possibility to talk on the topic of sustainability and building decarbonization via heat pumps. So today we hear a lot about sustainability everywhere in marketing and advertisements. The first recorded use of the word sustainability is dated 1713 in the Germany forestry circles, and it was defined by a guy called Van Karlowitz as the principle of harvesting as much as can be regrown in nature. In Europe, sustainability took the form of the Green Deal, the target of which is to achieve the Paris, the targets given by the Paris Agreement through strategy. The strategy consists of setting new targets for reduction of greenhouse emissions, increase the use of renewable energy, and finally become a net zero greenhouse gas emission economy by 2050. The execution consists of revised regulations and initiatives that have to do with the Energy Performance Building Directive, so-called EPBD, the Renewable Energy Directive, and when it comes to the HVAC sector, the F-gas and also the eco-design regulations come in place. Regarding the EPBD directive, we should consider that 85% of the European Union buildings were built before 2000, and 75% of them have a poor energy performance. Therefore, acting on the energy efficiency of the buildings is key to save energy, reducing bills for citizens and enterprises. Under the EPBD, there are targets for renovation of the non-residential buildings and sorry, just a second. And the residential buildings. For the non-residential buildings, you can see here in the app, there is a target to have 16% reduction in by 2030 and 26% reduction by 2033. For the residential buildings, each member state will be free to decide its own national trajectory, but what it is important to consider is that at least 55% of the primary energy reduction will have to be achieved through renovation of the worst performing buildings. Electrification is a big chapter in the European Union decarbonization process because the production and use of energy accounts for 75% of the European Union greenhouse gas emission, and therefore decarbonization is considered one of the pillars in the strategy. The Renewable Energy Directive is the legal framework for production of clean energy across the European Union, and it is, as I mentioned, a pillar to then decarbonize other sectors, mobility, of course, and for the sake of this presentation, heating. The Eco-Design Directive set new standards for more efficient use of energy. The Eco-Design introduced the seasonal energy efficiency indexes for chillers and heat pumps, as opposed to the full load efficiencies that we were used to consider in the past. We have two main regulations, 813, that applies to heat pumps reversible or heating only below 400 kilowatt. And we have regulation 2281 that applies to all sizes of chillers, to reversible heat pumps above 400 kilowatt and rooftops. Compliance to these regulations is a mandatory requirement to supply products with CE certification, and both revisions are ongoing with more stringent requirements. When we come to the F-gas, first of all, GWP is an estimation of the equivalent global warming effect of a substance, and it is expressed as the global warming produced from 1 kilogram of that substance. You can see top right, IPCC stands for International Panel for Climate Change, and this organization produces regular assessment reports to indicate the GWP effect of different substances in different time horizons of 20, 100, and 500 years. Now, the difference between the assessment reports is not a topic for this presentation, but for us it is just important to mention that the F-gas amendment is, the F-gas revision is based on the assessment report number 4, the first one in the left, that gives a GWP of 675 to the refrigerant R32. Why is this important? Because we will see that some of the limits for use of fluorinated gases have 750 as a threshold. If we go a little bit back in history of refrigerants. The first compression cycle using natural refrigerants was invented in 1834. After that, last century, between 1930 and 1950, we started to see the first chemical refrigerants. But then in the 70s, the ozone depletion process caused by chloride was discovered, and this brought to the first version of the Montreal Protocol on CFC and HCFC in 1987-1989. Then on the 90s, the global warming started to become a growing concern until the Kigali amendment of the Montreal Protocol 2016-2019 established a phase-down path for the HFC refrigerants. Now, if you look on the top diagram, this is the step-down quotas fixed by the Montreal Protocol for different groups of countries. Below, you can see in the table below in light green the step-down process in the US. In blue, the blue line is the first version of the F-gas, and the red line is the step-down of quotas. It means how much equivalent CO2 can be put in the market, taking 2015 as a baseline. And in red, the revision of the F-gas. So what it is important to underline that Europe started with this process of phasing down refrigerants even before the amendment of the Montreal Protocol, and the original version of the F-gas, the blue line, was already more ambitious, but then at least until 2030. The new revision of the F-gas in red sets the most challenging phase-down path that actually ends with a phase-out. But I mentioned that Europe was already more ambitious than the Montreal Protocol. Why the need for a new revision? Because this was valid until 2030. After 2030, the original version of the F-gas was not sufficiently strict to cover the requirements of the Kigali Amendment. And then there were also some additional users of fluorinated gases, particularly the medical inhalers, the device used for people suffering of asthma. Those also use fluorinated gas, and it was not coherent with the protocol agreements. The quotas for these medical inhalers were not coherent with the protocol agreements. Additionally, the F-gas establishes some new provision that have to do with including HFO on the leakage checks, enlarge training and certification programs and extending them to natural flammable refrigerants, fight against illegal refrigerants import, and improve and enlarge the refrigerant recovery and the reuse of the refrigerant. When we talk about bans on the new F-gas, we have this summary table. In red, you can see self-contained heat pumps, meaning monoblock heat pumps, not split. And for them, there is a limit from January 1st, 2027 of 50 kilowatt. All heat pumps below 50 kilowatt will have a max GWP permission of 150. From 2030, this limit will be extended to all capacities, And from 2032, all heat pumps below 12 kilowatt will have no F-gas permission. It's mentioned the safety exception here. It's not 100% clear, but it means that in case it is not possible to safely install refrigerants below 150 kilowatt, 150 GWP, sorry, then it will be possible to go up to 750. But that will require an assessment, and it will be responsibility of the local designer or installer or contractor to specify the absence of safe conditions to install lower GWP refrigerants. For chillers, for cooling only units, the limit starts from 1st of January 2027 and covers all capacities that will have a max GWP permission of 750. And you can see here, therefore, that the limit is much stricter for heat pumps than chillers. Also, the phase down is important because if you see in 2022, according to the F-gas report, the RACHP industry, refrigeration, air conditioning and heat pump, consumed around 72 million tons. Going forward in the future years, you will see that we will shortly have less than half of the quotas available. And we can also expect that this will put pressure on availability of higher GWP refrigerants and prices. This applies to the European Union, but why it is important also outside the European Union? First of all, because the same bans described in the upper table apply also to exported products with a GWP limit of 1,000. Second, because many manufacturers of chillers and heat pumps are located within the European Union and therefore affected by the limitations imposed. And third, because it will not be possible to ship units without refrigerants for the units to be filled locally. This will not be allowed. And finally, in terms of additional provision, new refrigerant tax, stricter measures for leaks checks, expand knowledge on flammable refrigerants, and some very high GWP refrigerants over 2,500 will be banned also for servicing existing units. But then it's not only the GWP that we have to be concerned. We also have the topic of the forever chemicals, the PFAS, okay, defined as those substances that contains CF2 and CF3. There is another European Commission working on the proposal to ban PFAS that would basically exclude all fluorinated gas with the exception of R32 and a few others. On this, Europe is taking a different approach compared to the United States. In Europe, the ECHA, the European Chemical Agency, is proposing a large Rreach restriction proposal that applies to more than 10,000 substances. In the United States, the EPA, the Environmental Protection Agency, has no refrigerant fluid included in the ban proposal. But what is the concern? The outcome of this chemical agency's investigation is that refrigerants like 1234YF, which is the refrigerant typically used in the air conditioning of cars, when released to the atmosphere and heat by the sun radiation degrades into an acid, TFA, trifluoroacetic something, okay, that enters the water cycle, pollutes the water, and the worst thing remains forever chemicals, okay? So there is a big debate about the possible effects on the human health. The expectation for Europe to act on this is around 2028, 2029. It's a different commission from the one that worked on the F-gas, but yeah, this is also something that we can expect in the future. And therefore, we think for Europe, the long-term strategy is to go back to natural refrigerants from where we started. We can see this already happening, starting from the residential sector, but also quickly moving to larger applications. The second part of the presentation has to do with heat pumps, TEWI, I will mention in a second, and good practices. So, having seen the legal framework and the evolving situation with regulations and legislation, we can now look a little bit into the heat pumps technology to say that heat pumps, from a sustainability point of view, address the key areas of eliminating fossil fuels, offering higher efficiency and lower primary energy compared to boilers, electrify heating taking advantage of renewables, and offer integration with the smart grid. It means that in some countries heat pumps take incentives if they are controlled by the grid and operated in response to price signals depending on the status of the grid. Heat pumps can be compared from a sustainability point of view in an objective way using an index called TEWI that stands for a total equivalent warming impact. TEWI is done of direct emissions and indirect emissions. Direct emissions are made of two components, one linked to the yearly leakage rate and one depending on the recovery factor. Indirect emissions are made of three components. One is the emissions due to the electrical consumption. Two are the emissions due to the unit production, maintenance, and disposal. And three are the emissions due to fossil fuel consumption. For us, the emission number 3 is 0, because when we calculate the requirements for integration source below the equivalent temperature, we consider electrical integration source in our calculations. The emissions due to the electrical consumption, of course, depend from the service life in years, from the total electrical energy consumption consumed by the unit, and this can be calculated in our case with the energy analysis tool made available by the calculation software, or using the seasonal energy efficiency indexes for heating SCOP, for cooling SEER, together with the EN 14825 load profile. And then there is a coefficient, B, the CO2 emission intensity for electricity generation that is variable from country to country and depends on the specific country energy policy and the use of renewable. You can see figures for some countries here, and we will also see the specific Serbian figures in a second. So in Europe, we go from the lowest figure of 8 in Sweden that takes advantage mainly of nuclear and hydropower. There is an average European Union figure of 275, and the highest are Poland and Estonia. The second element in the TEWI indirect emissions are due to the unit production, maintenance and disposal. Here the parameters that come in play is the mass, the weight, the physical weight of the equipment, and to the conversion factor C. This is a parameter that it is very difficult to estimate. There are some references in literature, but yeah, it's a bit, always a bit difficult. Therefore, sometimes we say that we calculate TEWI only considering the electrical consumption. For Serbia, this is the situation. There is a website mentioned down there that offers all the details regarding the energy mix of different countries, and for Serbia the index is 615 grams, meaning that there are 615 grams of CO2 released to the atmosphere for every kilowatt hour of electricity produced. Okay? Then the regulation also define different climatic zones in Europe, average, warmer and colder climatic region, and for each of these 3 regions there is a bin temperature profiles that is given by the norm. What does it mean? It means that for every external temperature that you can see in the horizontal axis, the column, the height of the column represent the number of hours during the year that you have at that external temperature. So the sum of all the columns makes 8,760. But you have to trust, of course, unless you want to try. So, if we take one unit from our legacy product range, ZREV HP XT 18.4, and we compare with the unit from new generation, Z0 20.6, they both have an heating capacity at nominal conditions of around 200 kilowatt. ZREV use 14A as a refrigerant with a GWP of 2088. Z0 uses propane with a GWP of 3. There is a significant reduction also on the refrigerant charge due to new technologies in place, but also different physical properties of the refrigerant. And we use on ZREV vapor injection scroll technology, and on Z0 are 290 optimized compressors for heating. The direct emissions, the first part of the TEWI index, reduced by 99%, when we compare the first with the second. The indirect emission for energy consumption, they decrease by 10%. And this means that in terms of TEWI, we have a 13% reduction for the new unit compared to the legacy unit. This is an example within our product range, but of course the same principle can be used to compare different heat pumps from a sustainability point of view. Now, changing topic a little bit regarding how to size heat pumps. This red line represents the load variation assumed by the normative for an average climate, from 100% of load at -10 to 0% at 16 degrees, meaning around 385% decrease every degree. We know that the capacity of heat pumps depends on the external ambient temperature, and the heating capacity decreases with the reduction of the external ambient temperature as for the blue line. This decrease, we could say more or less, it's not written on stone, but we could say more or less every 2% decrease every degree of external ambient temperature, with a 10% drop when we start the defrost. At some below a certain ambient temperature, the unit will periodically need to defrost. These graphs also give us another parameter where the two lines crosses, the heating capacity is equal to the load, meaning that below that temperature, the capacity of the heat pump is not sufficient and we need an integration source. Above that figure, the heating capacity exceeds the load. This is called ambivalent temperature, and it is very important to select it properly, because if we take this example, you can see that the heating capacity, the orange line, meets the heating loads at the lowest temperature. In other words, in the worst possible conditions. We think this is not ideal, because then when the external ambient temperature increases, if we work with a constant water flow rate, then the delta T will increase till the point that it will be more than 10 degrees and the unit will not be operating in optimal conditions. Or if we reduce the water flow, then at some point we will go below the lowest possible figure for the water flow, and again the unit will stop. But even most important, in all the orange and red area, the unit will be working highly partialized. In simple words, taking a parallel with the automotive, it is like selecting a car, a very powerful car, that most of the times you will use in the traffic of Belgrade city center, and only a few hours per year in the German motorways. Okay? You can, but it's not optimal. Much better will be to size heat pumps with an intermediate bivalent temperature that will allow the heat pump to work in the entire working envelope with a minimum load of 33% at higher ambient temperatures. This is very important, and we think it's a typical mistake, meaning selecting the heat pump in the worst possible conditions. So, just doing a quick summary of this. If we select an higher bivalent temperature, we have seen that there will be some hours during the year that we cannot meet the heat load, okay? But then we could still cover the load, reducing the living water temperature produced. Or if it's a small number of hours, we can play with a good sizing of the water tanks, the water volumes of the circuit. Usually, a lot of designers tend to overrate the loads and oversize the units even at the highest point. So the loads calculation is generous and the unit selection is even more generous. Or in some cases, it may be more efficient to consider integrative heating sources below a certain temperature. At Swegon, we have developed a range of propane units. We have started a few years back and we have gained significant experience. To do so, we have hired consultants, told to institutions, we have searched the feedback from all stakeholders and studied normatives in details to get proper confidence regarding the safety implications. We think that nowadays, together with our partner EnergyNet, we have the right experience, knowledge, range of products, and also capability to work on system solutions to support customers on their decarbonization agenda. We currently have one of the largest portfolio with propane, and all our units are Eurovent certified. We started in 2021, and we now have more than 600 propane units installed, result of building the knowledge internally and spreading, talking to local consultants, and also firefighting institutions to understand the local regulations better. We have the Titan family that includes our air source products with reciprocating full inverter units covering capacities from 300 to 400 kilowatt. The Titan Sky was the first born up to 200 kilowatt, and we have recently released the Titan Zero HI to cover the capacities up to 400. Main features for this range, they are optimized for heating mode, meaning that the heat exchangers are designed to be counterflow in heating mode. We have a living water temperature max of 63 degrees down to -7, and the units can operate down to -20, still providing a 50 degrees living water temperature. We have cooling-only solutions with capability to produce water down to -15, and the ability to be completed with partial or total heat recovery solutions. Free cooling versions where we use a solution with separate coils, not condenser and free cooling coils facing one the other, but separate, so that the free cooling fans can be run at maximum speed to optimize the free cooling performance whenever possible, and we can integrate free cooling non-glycol executions. And then we have the Zeta family, air source, reversible heat pumps, scroll or scroll inverter depending on capacity, from 30 to 230 kilowatt. This is, let's say, also one of our main ranges and main areas of business. And here we can see capability to work up to 75 degrees of living water temperature and operation till -20. We have also integrated a function called XR that reduce the loss of capacity at lower ambient temperature. Of course, as we have seen a few moments ago, the reduction in heating capacity is typical of heat pumps, but with this XR function, we are able to mitigate through an additional heat exchanger in the refrigerant circuit that works as a regenerative heat exchanger. And finally, we have our range of multifunctional units, 11 sizes from 50 to 200 kilowatt. We have developed quite a lot of experience also on multifunctional units, also here in Serbia with EnergyNet for projects that typically see contemporaneity of heating and cooling demands. So, if we come to some conclusion, some of the main takeaways for today are: we must use sustainable solution that minimize the carbon emission and make use of renewable energy. The heat pumps technology answers this challenge very well. Heat pumps are, however, not all the same. And from a sustainability point of view, they can be compared in a objective, non-debatable way using the TEWI index that calculates both the direct emissions and the indirect emissions. We have seen that the indirect emissions are also linked to the specific country energy policy. The European electricity carbon intensity is dropping. So this means that heat pumps become day by day more sustainable and will be able to contribute to the European decarbonization targets. Thank you.